Okay, this is 4-13, factoring quadratic expressions. So a polynomial in the form ax squared plus bx plus c with a not equal to 0 is called a quadratic expression in standard form. And we're going to develop a method for factoring these expressions using algebra tiles and then our area models. So in part A, it says use the algebra tiles below to factor 2x squared plus 5x plus 3. That is, write its area as a product. So remember from before. So we have our diagram set up here with the algebra tiles in a rectangular formation, which is necessary for it to factor. And then in order to write it in factored form, like this format with the length and the width of the rectangle, we need the edge lengths. So remember, the large x squared is an x by x. This would be an x also. These little lengths are ones. And now I can collect my information and write my factors. So along the bottom, I have x plus 1 plus 1 plus 1, which is 2 x's, and plus 3 ones. And then on the other edge, I have x plus 1. So there's my factored form. All right. Now, I'm going to go to part B. There we go. So when you factor using tiles, you need to determine how to arrange the tiles to form a rectangle. Using an area model to factor requires a slightly different process. Miguel wants to use an area model to factor 3x squared plus 10x plus 8. He knows that 3x squared and 8 go into the rectangle along one of the diagonals. You can see them here, diagonals. And then finish the rectangle by deciding how to split and place the remaining term. Then write the area as a product. Okay, so remember, the diagonal products need to be equal. There's that pattern we learned from before. So 3x squared times 8 is 24x squared. So however I put numbers into the other two boxes, they have to multiply to be this. But then looking at the original equation, the original expression up here, we want the remaining terms, the stuff that hasn't been put into the box yet are the 10x's. So we're trying to break down the 10x's here and here. So we need them to add up to be 10x. So we need a product that is 24x squared, but we need the two terms that we pick to have a sum of 10x. So thinking about all the ways I can make 24, I could go 12 times 2 or 6, I don't know, 6 times 4 or 3 times 8. And it looks like 6 times 4 has a 6, so a 6x and a 4x. And 6x plus 4x would make 10x, but 6x times 4x would make 24x. So these are the two we want. So I'm going to put a 6x here and a 4x here. And now this is going to see how, if we added up everything inside the area model, we would get the original equation or expression, excuse me. But now if we get the side links, we will get the factored form. So now along the edges, I'm going to put a 3x here because both those two numbers, 6x and 3x squared, are divisible by 3 and x. I'm going to put an x here. X times 4 makes 4x, and 3x times 2 makes 6x, and 2 times 4 makes 8. And now we have everything we need. So our factored form would look like along the bottom, 3x plus 4, and along the side, x plus 2. And we're done. Okay, now that seemed like a little bit of a messy way to organize things. So, we're going to learn a little bit more like careful way of organizing our work. All right, part C. Kelly wants to determine a method for factoring 2x squared plus 7x plus 6. She remembers Casey's pattern for diagonals. She places 2x squared and 6 into the rectangle in the locations here down below. Without actually factoring yet, what do you know about the missing two parts of the area model? So what we know is that, we know that the product, that's multiply, of the missing diagonals must be 12x squared. I don't know if I can get, I guess I'm just gonna go ahead, 12x, where's my caret, to the second power. Oh my goodness, that looks like a mess. And that the two terms must have a sum, this is when we add, of 7x, which is the number inside or in the middle. This, it's the number, the missing term in the original expression. All right, so this is what we know. This is, by the way, this is 12x squared. I just didn't have a way to make an exponent on my notation. Okay, so those are the things we know. We know that this times this has to be, or is 12x squared. So then this product has to be the same. And then we also know that the two numbers have to add up to 7x to make the original expression. Okay, so this is how we can organize this. So see this thing up here, we're gonna call this the diamond. And we've done a couple of these in our homework in the past. So in this diamond, what I'm gonna do is I am going to put the number I want as a product. So remember, 2x squared times 6, that diagonal is 12x squared. I'm going to put 12x squared in the top of the diamond. That's the product I want. See how it says product? And then I'm going to put 7x, the middle term that we haven't filled in from the area in the bottom. This is the sum that we want. And now using this as an organizational tool, we're going to find two numbers that fulfill both of these criteria. So let's think about all the ways we can make a product that's 12. So I can go 12 times 1. I can go 2 times 6, 3 times 4. And I see that 3 times 4 makes 12, and 3 plus 4 would be 7. So this is what I'm going to use. I'm going to use 3x and 4x to complete my diamond, because 3x times 4x makes 12x squared, and 3x plus 4x makes 7x. And those are the two numbers that fill in my area model down here. So, oops, don't erase that. So 3x and 4x would complete the area model. And then finally, we get to factor. So I'm going to go ahead and find my edge lengths. So I know that 2x squared and 3x, the only thing they have in common is x. But 2x squared and 4x have 2x in common. 2x makes 2x squared, so we're good there. X times 3 makes 3x, and 2x times 2 makes 4x. So these are my edges. And finally, I can write my factors as I have x plus 2 along the bottom, and I have 2x plus 3 along the side, and I'm done. Okay, so let's do this one more time. Factoring with an area model is especially convenient with algebra tiles when the algebra tiles are not available, or when the number of necessary tiles becomes too large to manage. So using a diamond problem helps avoid guessing and checking, which can at times be challenging. Use the process from 4-13 to factor this expression here. Oops. this expression here, 6x squared plus 17x plus 12. All right, so to begin, we always start with our first term and our last term as diagonals in our area model. Okay, and then before we can decide how to split up the 17x to fit in the two other squares, we need to figure out what their product will be in the area model. So 6x squared times 12 is 72x squared. So 72x squared is the product we want. And then we want the sum to be this middle number, 17x. And we're going to split up the 17 and put some of it here and some of it here in the area model. So now we need two numbers that multiply to be 72x squared, but add to be 17x. And so we think about ways to make 72. I can multiply to be 72 using 36 times 2. I can use 18 times 4. I can use 9 times 8. And look at that, 9 and 8 would make 17 if we added them. So I have 9x and 8x here. They multiply to be 72x squared, but they add to be 17x. And then I go ahead and fill those into my area model. And then finally, I get my edge lengths. So I notice that 9x and 6x squared both are divisible by 3 and by x. And then to make 6x squared, 3x times 2x would make 6x squared. And I know that 2x times 4 would make 8x. And I know that 3x times 3 would make 9x. So then, and then 3 times 4 is 12. We're good. That works. So here is our factor written as a product factored form. 3x plus 4 along the bottom and 2x plus 3 along the side.